the two problems that we will be looking at today are the longest common subsequence and the longest common substring. Okay. So last time we introduced dynamic programming. The question is how would you describe dynamic programming? What characterizes the dynamic programming algorithmic technique? How would you characterize it?
We start with solving smaller subproblems, and then with the results of the smaller subproblems, we try to complete the bigger problem and follow bottom to top approach.
Yes. Okay. So the idea is to solve smaller subproblems first, starting with very easy base problems or base sizes. And another key idea is storing the results of the solved subproblems in a table. And what's the purpose of storing those in a table? Yeah, reusing them instead of recomputing them. That can save a lot of computation time. As we have seen with the Fibonacci example, if you recompute, that can result in huge explosion in the number of operations. But if you just store the results of the subproblems and reuse them, that can save you a lot of computation, and the overall running time is going to be much better. Okay, now let's introduce the longest common subsequence and the longest common substring. So basically, if you have a string, two strings, string x, which is A, B, C, D, E, and string y, B, D, A, E. Now, a common subsequence of these two strings is any sequence that is common to both, that appears in both, and a sequence doesn't have to be contiguous. So a common substring is obvious, right? You find a common substring like here. What's the longest common substring between these two?
No.
DE? BDE?
Yeah.
Well, BDE. So is BDE a longest common substring or a longest common subsequence? Subsequence, yeah. So BDE is a longest common subsequence. Subsequence. So in a subsequence, we can skip characters. The sequence does not have to be contiguous, while the string has to be contiguous. So in this case, in fact, this could be a bad example. Do we have a common substring that is longer than one? No, I didn't think so. But for example, if we have CD, for example, or here we have, so we can add, for example, if we add C here and C here, then this will be a longest common substring. So the string has to be contiguous, but the sequence does not have to be contiguous. Now, which problem will we try to solve first using dynamic programming? First, we will try to solve the longest common subsequence. So given two strings, try to find the longest common subsequence where you can skip. Okay. So now, if before we start talking about the dynamic programming, what would a brute force solution to this be? Can you describe a brute force solution?
Just go through each and compare 'em.
Each what?
Go through each and compare.
Each what?
I'll grab the shortest and compare that to the longest.
So you'll have, look at X, you find all possible subsequences. So how many possible subsequences are there? If there are m,
Factorial.
no, it's not going to be m factorial. What's the total number of subsequences? No, it's not m factorial. Given that X has m characters or m symbols, how many subsequences will we have?
2 raised to 5.
Yeah, 2 power my.
The power.
Yeah, because each character is either taken or not taken in the subsequence. So the subsequence is just a subset of these characters, right? So you have 2 power m. So this is not a good start at all. So this is already exponential. But this is not enough, right? We'll have to find all possible subsequences, and then for each subsequence, we'll have to find it in the other string to see if it's there or not. And then we take the longest. So obviously this is going to be, at best exponential. In fact, it's more than exponential, because you'll have to search for each subsequence in this string. Now let's think of this in terms of dynamic programming, in terms of smaller subproblems and larger subproblems. So I think the best way to think of a dynamic programming solution to a problem is to assume that you have solved the smaller subproblems and see how solving smaller subproblems can help you solve bigger problems. Okay? Base cases are not a problem, because you can always find easy base cases. Like in this case, if the strings are empty, then the longest common subsequence is empty. That could be a base case. Or if each string has one character, then the longest common subsequence is what? It will be that character if it's the same, and it would be empty if that character is different. Anyway, so you can easily find base cases. But what is not easy to find is thinking in dynamic programming, where you assume that you have found the solutions to smaller subproblems, and you are interested in finding solutions to bigger problems. So for example, what if I have these strings A, B, C, D, and A, C, B, D. Now let's assume that this is string X and this is string Y, and at this point you are trying to find the longest common subsequence between and then there are other characters, but this is character I and this is character J. So now you are trying to find the longest common subsequence between X sub I and Y sub J. Now the way you think of this in dynamic programming is to assume that you have found the solutions to the subproblems. So the subproblem here is, for example, this. You assume that you know the longest common subsequence between, so this is I minus 1 and this is J minus 1. Dynamic programming wise, you will assume that I know the solution to this and the solution to this. All right? So now what's the solution to the big problem? Well, in this case, obviously, the solution to the subproblem is what? So you have ABC. What's the solution? AB or AC. AB or AC. So the solution here is not unique. There are multiple solutions, multiple optimal solutions. So for example, let's assume that it's AC. Now we assume that this is known. In dynamic programming, we assume that this is known. Given that we know this, what's the longest common subsequence now between xi and yj? So now we can add d to this. So we have the longest common subsequence is ac. Now we can add d. So this is clear. If you are trying, if you are at index I in string x and at index j in string y, then you can look at the subproblem that you have solved previously, and you just add this character to it. Under what condition? They're the same. Yeah. So if they're the same, if this and this are the same, then we just add the character to it. So we can express this as longest common subsequence of I and j equals, or use more space, longest common subsequence of I and j equals longest common subsequence of I minus 1, j minus 1, plus 1. So L here is the length of the longest common subsequence. Is the length, not the actual characters. This is the length of it. Is plus 1 if what? If x of I equals y of j. If x of I equals y of j. But now what if they are not equal? So let's look at this example. xi equals a, b, c, d, and yj equals ba, da. Now, while we assume that we know the solution to this subproblem, the subproblem of the longest common subsequence between this and, so this is I minus 1, this is j minus 1. Now, if these are not equal, what's the length of the longest common subsequence between xi and yj? Is it going to be just the, is it going to be just the solution to this subproblem, the solution which is longest common subsequence of I minus 1, j minus 1? Okay, so now let's look at this. Let's look at the longest common subsequence between I minus 1 and j minus 1. What's the length of this subsequence? So in this case, you have a, b. So the length is going to be 1, right? Between this and this. But is the length of the longest common subsequence between this 4-character string and this 4-character string, is the length 1? Here is the length 1. What's the length of the longest common subsequence between?
Whole string or?
No. Between the 4 and the 4. 2. Between. So in other words, we cannot say that the longest common subsequence of I and j equals longest common subsequence of I minus 1, j minus 1, if x of I is not equal to y and j, to y of j. So this is wrong, right? This cannot be right, because if this is true, then it will give us here 1, while the right answer is 2. So what should the right answer then be? How can we compute the right answer in this case? Think of solutions to subproblems. So the subproblems do not necessarily have to be, x of I minus 1 and j minus 1. Think of other subproblems.
We can implement I.
Yeah, exactly. So you can think of the longest common subsequence between I and j minus 1 and the longest common subsequence of I minus 1 and j. These are two subproblems that are relevant. So I and j minus 1, this is going to be what? This is going to be these four. This is I, and this is j minus 1. What's the length of the longest common subsequence here? 2. So this is this and this. 2. So this is I and j minus 1. Now, what is what if we do it the other way around? What if we do j and I minus 1? Is it going to be the same? So this is j and this is I minus 1. What's the longest common subsequence? 1. Okay. So now this is not true. If x of I is not equal to I of j, the longest common subsequence is not going to be the longest common subsequence of I minus 1 and j minus 1. So this is wrong. But what should it be? What should we write here? What's the how can we get the right answer? Generalize this.
Max of this two.
Yeah, the maximum of these two. The best of these two. So looking at I minus 1 and j minus 1 will not be enough. If we look at this and this, which will give us 1, then we look at this with this, and that will give us 2. 2 is better than 1, so we will take this. So to generalize this, longest common subsequence of I and j is the maximum of longest common subsequence of I minus 1 and j and longest common subsequence of I and j minus 1 if what? X of I is not equal to I of j. So we have two cases. If x of I is equal to I and j, that's easy. We extend the previous and add 1. If they're not equal, we look at these two possibilities and take the best. And of course, we need a base case. So the base case is easy. So if one of them is empty, then the longest common subsequence is empty. So this is an easy base case. So this is going to be 0 if I equals 0 or j equals 0. So we start numbering from 1 here. So this is going to be 1, 2, 3, 4. So if one of them is empty, then this is a base case. The longest common subsequence is going to be empty. Okay. So this is the algorithm. So let's write the code for this. The code is going to be, the heart of the code is going to be this formula, which we call the recurrence for this dynamic programming solution. So basically, the key idea in any dynamic programming solution is how to define the solution to a big problem in terms of the solutions to smaller subproblems. Okay, so that's the key idea in any dynamic programming solution. So now, yeah, let's go through an example first. Let's go through an example. So So the example is here none and none, and then we have x is a, b, c, a, b, c, b, d. This is x. So this is x of I. And this is y of j. So j goes, j is the column number. A, B, C, B, D. And this is B, D, C, A, B, D, C, A, B. So this is going to be our table. Obviously here, the cell T of I and J is the longest common subsequence, or the length of the longest common subsequence between xi and yj. xi is the string through I, and yj is the string from the beginning through j. Okay, so in the beginning we can fill this row with zeros, because when x is empty, this is going to be empty, 0. Then, now we have A. Now, we can also fill the first column with 0. Because when y is empty, the longest common subsequence is going to be empty. Now, when we go through each cell and we compare the two characters, if they are equal, we apply this. If they are not equal, we apply this. So these are not equal. So we'll apply this. So where is longest common subsequence of I minus 1 and j? I minus 1 and j, that's going to be the above, the row above. So I minus 1 is the row above, same column. This is same row, the column before. Okay, so we look at this and this, these two guys, and take the larger. Now if they are equal, we'll have to systematically pick one of them. So let's say it doesn't matter. If they are equal, you can take either one. Let's systematically take the one from the previous row, if they are equal. Okay, so now this is going to be 0. Again, not equal. We look at the row above and at the column before and take the larger. They are the same, so we take the row above. And that's going to give us what? 0. Same thing here, because they are different, so we'll get the same thing. Now they are the same. When they are the same, we apply this. So where will we find L of I minus 1 and L of j, longest common subsequence of I minus 1 and j minus 1? So it's going to be diagonal, right? Yeah, so it's going to be diagonal, this. So we look at this and we add 1 to it. Okay. Now these are different. So again, we compare the row above with the column before. Now which one is greater?
1.
The column before. So we take the 1. Now these are equal, so it's diagonal because they are equal. And that's going to be 1. Different, which one is greater? The column before, so this is going to be 1. Different, again, this is greater, so this is going to be 1. Different, so both are equal, right? So we take one of them, so let's systematically take the row above. Equal, we go diagonal. And that's going to be 2. Okay? Now, B and C different, so we take the 1. Different, we take the 1. Similar, diagonal, we put 2. Different, we take the 2. Different, we take the 2. Similar, diagonal. Different, we take the 1. Different, we take the 2. Different, but these are the same, so we take the 2. Similar, we take diagonal. This is 3. Okay? Last row, different, we take this. Similar, we go diagonal. Different, 2, and different, 2, and different, we take the 3. Okay, so this is how we fill in the table. So now we know the answer. What's the length of the longest common subsequence? 3. We know that the length of the longest common subsequence is 3. But now, which characters did we take? Now we have to do something to some kind of traceback, like we did with the 0-1 knapsack problem, trying to figure out which ones got taken and which ones did not get taken. So in this case, what indicates whether a character got taken or not?
Diagonal.
Yeah, whether it's diagonal, right? So we can store these, diagonal or not diagonal. We can store this, but without storing it, we will know, right? So let's assume that that in this case we store we store in each cell whether we went diagonal or we took from the previous row or the previous column. So here, since we took this from 3, right? So we just go up. We did not pick the D. We go to the previous row. So since this is not diagonal, we did not pick the D. Now here there is diagonal, so we picked the B. Then that leads us to this square. Now, is this diagonal? No. It's not diagonal. In fact, we can, without storing diagonal or not diagonal, how can we tell, by the way? Whether it's diagonal or not diagonal, how can we tell without storing?
Check the top one to the left and one above and see if it's the same as the number. And if it's not,
compare the characters, right? So for example, in this last column, we know that it's not diagonal because this is a D and this is a B. So if the corresponding characters are not equal, we know it's not diagonal. Anyway, so now we are here and the characters are different. This is an A and this is a C. So this cannot be diagonal. So we'll go to this. So this means that the C did not get taken. Now, this is diagonal. What does it mean? The C is in. Okay, so now we go to this. Again, B and D are not the same, so it's not diagonal. So we're going to the 1. So we go to the 1. Now, B and B are the same. So we are here. Then we go to diagonal to this. And now we are at 0. So we know that, well, that this is a base case. So we just stop. If we reach a base case, then we can stop. Okay, so now we know that what the longest common subsequence is B, B, C, B. Okay, so this is based on what we have taken. Okay. Okay, and in many cases, the longest common subsequence will not be unique. There may be multiple longest common subsequences. So is it clear how we trace this? So basically, the diagonal, whether we store diagonal in each cell or we just compare the two characters. If they are the same, then we take them. If they are not the same, then we go to the row above or the column before, depending on which one is greater. And if they are equal, we can go to either one. Okay, now let's translate this into code. Longest common subsequence of x and y. So let m equals x dot length and m equals y dot length. Then we create a two-dimensional array, call it T, with m plus 1 rows and n plus 1 columns. Is this problem symmetrical? So what if we put x in the columns and y in the rows? Will it still work?
Yes.
Yeah. They're just two strings, right? They are indistinguishable. Just two different strings. You can treat either one as x or y. It doesn't matter. So we create a two-dimensional array. Then fill the first row and the first column with zeros. Okay? Then, what kind of loop will we have here? This is a two-dimensional array. So we'll have a nested loop, right? One that goes through the rows and one that goes through the columns. So just a two-dimensional array. So we'll go for I equals 1 to m, and for j equals 1 to n. In fact, we just put that formula that that I have just erased. So if what? X of I equals y of j, we apply the rule of t of I and j equals what?
X of I.
Not x. T
I
I minus 1 and j minus 1 plus 1. Okay? else, if they are not equal, then T of I and j equals what? Maximum of
I minus 1j.
T of I minus 1 and j, T of I j minus 1. And that's it for building the table. Okay. Of course, you know, if we were to expand this max, what would this max expand into? If we were to expand it, what would this translate? This T equals max. How would you, if you were to code this, how would you code it?
If T of I minus 1 is greater than.
Yeah. So it's going to be an if else. So if this is greater than this, take the answer is this. Otherwise, the answer is that. Okay. So in fact, the details of coding this into an if else will determine if when they are equal, it will determine what will happen when they are equal. Right? So if you say that, for example, if T of I minus 1 and j is greater than T of I j minus 1, then T of I and j equals T of I minus 1 and j, else T of I and j equals T of I j minus 1. Now, if we implement it like this, what will happen if they are equal?
It will execute the else.
To the else. We will execute the else, and the else goes to the previous row or the previous column. Previous. So this is the same row, previous column. So this is previous column. So in fact, if we implement it like this, it will be the opposite of what we were doing. We were going to the previous row. So here, we're going to the previous column. Yeah.
So it will be that if else statement will be in the under the else part, right? Of x of I equals j of y of j.
No, this is still there. So we are replacing this thing. We are expanding this. So this if else is an expansion of this. So this if is still there. This is still there. We're not touching this. So we're only replacing this line with these 3 or 4 lines. Okay?
We'd have to look up how max is implemented in the library, or how we choose to implement max.
Well, you know, max is, you know, too easy to require a library, or you can implement it yourself. You know, you can implement the max yourself because it's trivial. So if you want to control it, you write your own max. So if we want to take the previous column, it's like this. But if you want to take the previous row, you can, for example, do this. If you do this, then the equality will go to the previous row. Right? So you control it. But both are correct. Right? When they are equal, you can go either way. Now, what's the running time of this? This is theta of nm. Now, is this polynomial? So is this like the knapsack, or it's how? Is this like the knapsack? Are m and n, are they numbers, or they are actual sizes of objects that you are passing as input? So they are actual sizes, right? So they are the size. So the actual input is going to be the string. So it's going to be this thing. So this is the input, this string and this string. So m and n are just the sizes of these. So the input has n and the output has, this dimension of the input is m and this dimension is n. So the mathematical relation between the input size and the number of iterations is linear. The number of iterations of this loop is a linear function of the input size, which is the number of these characters. And here, the mathematical relation between the number of iterations and the number of characters in the input is a linear. So this is polynomial. Okay. So now what remains is writing code to, yeah.
So since it's polynomial, does that mean that complexity is big theta just n? Or
No, it's nm. So the input is defined by two parameters. So there are two strings at the input. So it's nm. So it's a function of two variables. It's a function of two variables, but it's polynomial. It's a polynomial function of these two variables. We don't have.
is it linear?
No.
Oh.
No, it's not. So this is not linear. It's not linear. It's not a linear function of the overall input. It's just it's linear. The number of iterations of this is a linear function of this. But this overall running time is not linear. And thank you for asking. So this is not linear, but it's polynomial. The overall running time is not linear, but it's polynomial. Now we need to write code for tracing back. Tracing back to identify the characters that got taken. So now we'll have to start from the last square, right? Like we did here. So we just say, okay, so find characters, or not find characters. It's not a good name. Yeah, construct the string. Construct the longest common subsequence. And this should run after this. So after we construct the table, we construct the string by starting from this square. So we set I equals m and j equals n. What does it mean? It means that we start from this. Then, when do we stop? In fact, we keep going as long as we have, both of them are greater than or equal. Both indices are greater than or equal to 1. So while I is greater than or equal to 1 and j is greater than or equal to 1. Now if what? So what did we check on? If the two characters are equal. So if x of I equals y of j, what do we do? We take it, yeah, exactly. Take x of I, or put it in the string, add it to the string. Or let's say concat or add x of I to the string, to the longest common subsequence. Then what? Then we have to go diagonal. How do we go diagonal? Yeah, exactly. So I minus minus, j minus minus. Now else, if what? Now we have to do this. If t of I minus 1, t of I minus 1, and j is greater than or equal, whatever, t of I and j minus 1, then we go to the previous row, which means what? Yeah, I minus minus. Else, j minus minus. And that's it. So what does it mean? It means that if we compare the two characters, if they are equal, we take the character and we go diagonal. If they are not equal, we see which of these is greater. If this is greater, we go to the previous row, but we do not take any characters. So we just move. Now the question is, what's the running time of this algorithm? So look at this table. When we trace back, what's the worst case asymptotic complexity of this? M? So M is this. It's more than M, obviously. So we don't go straight. So we don't go this way or we don't go this way. So it's greater than M and greater than N. But is it Mn?
It's M plus N.
Yeah, exactly. So this is M plus N. Okay. So it's, in fact, here it's, it's easier to say it's big O of M plus N. So we know that it's not going to exceed. We know that it's not going to exceed M plus N. Why? Because in each move that you make, you either increment M or you either decrement I or decrement J. So in every step that you make, you either decrement I or J or both. So this is going to be O of M plus N. It's not going to exceed M plus N. Okay? You are guaranteed to decrement at least one of I and J. Okay. So this is the algorithm here. And this is how we construct the longest common subsequence. Okay. Any questions? So let's talk about the longest common substring. In fact, the dynamic programming solution to the longest common substring that we are about to describe is not the best algorithm for finding the longest common substring. The best algorithms for longest common substrings can be developed using what we call the suffix tree. So suffix trees can be used to develop or to develop algorithms that are much more efficient than the dynamic programming algorithm that we are about to describe. But we will study this algorithm anyway as an application of dynamic programming. But just I want you to know that this is not the most efficient. So in terms of longest common substring, again, think of the problem this way. I have, say, A, B, C, and here this is X, this is Y, this is A, B, C, and I have A, B, C here, and then I hit X and Y. So this is I and this is J. Now I'm at index I in X and at index Y in J. Now clearly, if I have this substring ABC, clearly if X equals Y, then this is going to give me a longest common substring of size 4. So if X equals Y here, then this will get concatenated to both strings, and it will give me a longer substring of size 4. So we know that if if x equals y, then we will get something like this. In fact, I'm going to keep the same code because it's going to be the same. So, but this will be different. So now longest common S stands for substring. But now what if I and j are not equal? Now the difference between the longest common substring and the longest common subsequence is that in substrings I cannot skip. So assume that x and y are different characters. Now what if I have after this, for example, A, B, C, D and A, B, C, D? Now, the question is, since x and y are different, will the longest common substring between these two strings, will it include this ABC in it? No, because there is a discontinuity here. Remember, the string has to be contiguous. And if x and y are not equal, then basically when I hit two characters that are not equal, I will have to start over. So this is the best that I could construct up to this point. And then anything that comes after x and y, I will have to start over. I will have to start building a new common substring. I cannot concatenate to this because I already have this disconnect. These two characters that are not the same. So in fact, this simplifies the problem. If x and y are equal, I will do this. And if x and y are not equal, then the length of the longest common substring that ends at this point is going to be what? Well, it's the length of the longest common substring that ends at I minus 1 is this. So the longest common substring that ends at I minus 1 and j minus 1 is ABC. But at I and j, there is no common substring, in fact. So I have to start over. And I have to start looking again for similarities. So in fact, what I can do here, if they're not equal, then T of I and j equals 0. What does the 0 mean? It means that when I hit two characters that are not the same, I will have to start constructing a new longest common substring. I cannot build on the previous longest common substring because the string must be contiguous. Okay? Now, this will make more sense if we do an example. Okay, so let's use this example, BC ABC let's use this example, A, B, C, D, E, and B, C, B, C, D, A, E. And now I'm gonna, we can just clean it up. Now it will make sense when we do this concrete example. So now, and I fill the, obviously when one of them is empty, then I don't have a longest common substring. I don't have anything. Now, not equal, just 0. Not equal, 0. 0. Equal, I go diagonal, right? So equal the same, we do the same that we were doing with longest common subsequence. So it's going to be diagonal. Not equal, simple, 0. Equal, go diagonal. 1. Not equal, 0. Not equal, 0. Not equal, 0. Not equal, 0. So there will be lots of zeros. Not equal, 0. Equal, what should I do? Diagonal. Not equal, 0, 0, 0. Not equal, 0, 0. Equal, diagonal. Oh, sorry, I put 3 here. I should have put what? 2. I need to put the length. So this is going to be what? 3. So these diagonals are going to point you to the longest common substring. Not equal, 0. Not equal, 0. Not equal, not equal, not equal. A and D not equal. Equal, diagonal. Okay. Now where is the longest common substring? So where is the is it in the last square? No. So the longest common substring, the answer will not be in the last square, not in this square. In fact, it will be the square that has the maximum. So I just keep track of the maximum. So in this case, I just keep track of the maximum. So for example, I define maximum I equals 0, maximum j equals 0, and maximum longest common subsequence equals 0. And then when I get this hit, I keep track of the maximum. So what should I do here? So let's move the else. So this is else t of I and j equals 0. Now what should I put here?
Max equals the max of previous max and
Exactly, yeah. Max of previous max, longest common substring, and
t sub I.
yeah, t of I and j. So I just keep track of the maximum. Well, in fact, I have to update I and j if this changes. So it's better to do it with an if statement. So let's do it with an if statement. So that I can change. If t of I and j is greater than the previous max common subsequence, then the max is now equals to t of I and j, and our I equals our max I equals I, and our max j equals j. So we just mark the I and j. So this way, when we go through this, our maximum will be this. Right? Now, how will we find the string? Will that be easier or harder than the longest common subsequence to find the actual string?
Easier.
Why is it easy? How can we find it?
previous number of.
Exactly. Yeah, so the length of the longest common substring is 3. So in fact, I just go 3 characters back in either string. So I either, I take these 3 characters, and they should be the same. So from this point, from this D, I go 3 characters back. D plus, 2 other characters. So since I know that the length is 3, I just go back by 3 characters in either string. So this should be trivial to implement. Now what's the running time of this algorithm? What's the running time of this? Yeah, so this is mn, same thing, it doesn't change. And the running time of constructing the string, obviously, it's not going to add. Because to construct the string, if you mark the maximum, then you go back by the length of the string, which will not exceed n or m. So it will be less than n and less than or equal to n and less than or equal to m. It has to be a string in both, a substring of both. So we will go by a number that will not exceed n or m, which means that it will not add to the asymptotic complexity. The asymptotic complexity will stay nm. Okay? So any questions on the longest common substring problem? Okay, again, this is a good application of dynamic programming, but this is not the most efficient algorithm for finding the longest common substring between 2 strings.